So basically we have three aspects of current that we want to discuss today. Batteries are rated by voltage, and voltage is basically how hard the battery is going to push the electrons through a circuit. You can think of it as force almost. We talked about, when we're discussing kinematics, we talked about how force is a push or a pull. Well, voltage is how hard the battery is going to push the electrons through the circuit. And the harder the push is, the more energy that current is going to carry. And we measure that in volts. You are probably familiar with AA batteries, regular A batteries, C batteries, D batteries. All of those are 1.5 volts. You can also get those kind of rectangular type of batteries. They're about this big, and those are 9-volt batteries. A car battery is generally 12 volts. And so that's are some common voltages for batteries that you're probably familiar with. And so I could get more energy by pushing harder on the electrons that are going through the circuit. I could also get more energy out of my circuit by making more electrons go through. And so how many electrons are going through in a second is going to increase the amount of energy that's being carried by that circuit as well. The more electrons that go by, the more energy that's carried. And current is measured in amps. Now, in order for a circuit to be dangerous, only one of these has to be high. So I had mentioned that a 9-volt battery is going to be in a toy. You can have a 12-volt battery in a car. But if you're playing with your toy that has a 9-volt battery and you kind of intercept maybe with your skin that current, you're not really going to hurt yourself too bad. But I know that we recently had a son who had a dead battery in his car, and he actually called here one evening and he said, "Dad, help me remember how to hook this up so that I can get my car jumped because I don't want to electrocute myself." So the voltage on a car battery isn't super high, especially if you compare it to the batteries that we commonly put in flashlights or alarm clocks or things like that. The difference is that there's a whole lot more current running through a car battery than there is another type of battery. And so if only one of these is high, the battery can be producing a very dangerous level of current. If both your voltage and your current are low, then the battery isn't nearly as likely to be dangerous for you. I also want to make a point on an electric circuit that may have confused you. It's sort of like if you have water coming out of a faucet. When I turn my faucet on, I don't have to wait for a particular water molecule to go all the way from my well out in the backyard, through the pump, through all the pipes, up through the house, and then coming out the faucet. As soon as I turn the faucet on, I get water coming out. And that's because there's already water in all of those pipes, and I turn the faucet off and the water just continues to sit there. So it's very similar to how electricity is going to run through a circuit, through a wire as well. The electrons are already all lined up on there, and as soon as you allow the circuit to start running, the electrons are going to be running right away. You don't have to wait for the electron to get from the negative terminal of the battery all the way to the positive terminal before you have a current flow. It's going to happen as soon as you get everything hooked up. Just like as soon as you turn your water faucet on, the current is going to, or the water is going to start to flow right away. So I just wanted to point that out so that you didn't think you had to wait for one electron to get all the way through before you had some current. Now, when we were talking about motion, we talked about how friction will impede motion. If you're playing sports and you're playing a type of sport where you're trying to get the ball from one end of the field to the other, the opposing team is going to try to resist you getting down there. They're going to try to impede your motion. They're going to try to get in your way so that you can't get the ball to the other end and score, or whatever sport you happen to be playing. I tend to think of soccer and football probably most often because that's what's most popular at our house. So especially on a soccer field. I know when my kids are playing soccer, if I've got a daughter who's trying to run down and get the ball in the goal, she's got players that are getting right smack in her way, trying to resist her motion, trying to impede her motion so that she can't get all of the way down the field and score. Well, you also have resistance to electrical power, and there are other particles that are going to get in the way of those electrons flowing. When you have too much resistance, what happens is that power starts to change form, and it can turn either into heat or light. So actually, this is one way that we harness the use of electrical power, is that if we have a circuit, we can put a type of resistor in it so that that power will be changed into another form. So things like a stove or a space heater are going to have materials in them that tend to resist the flow of electrons in such a way that heat is produced. If you take a light bulb and you screw it into an electrical circuit, that particular object, a light bulb, is going to have materials in it that are going to resist electrical flow in a way such that light is produced. So resistance isn't always a bad thing. It can be used in a good way for how we're going to get use out of some of our electrical power. Now, the amount of resistance that you have is going to depend on a number of different things. First of all, it depends on the type of material that you're going to use. We talked about how rubbers and plastics are going to resist the type of electrical current that we've been talking about. If you're talking about wires, though, it depends on the nature of the wire. The wider that the wire is, the more space that the electrons have to spread out, and so the less likely they are to run into other things. So the wider your wire is, the lower the resistance is. So the bigger the diameter, the lower the resistance. If you have a really, really long piece of wire, though, your resistance is going to go up because the electrons just have that much more of a chance of running into something the whole time that they're trying to travel down the wire to get to their destination. So you can increase the width, and that's going to lower your resistance, but if you make it really long, you're going to increase your resistance. That's why a lot of times if you string together too many extension cords, the amount of power you have once you get down to the end is going to be lower than maybe you would hope for because there's been too much resistance because you've used too many extension cords all strung together. Finally, and this is going to depend again on the material that you're using, but temperature is going to increase resistance as well. The higher the temperature, the more your particles are moving around, and so the more likely they are to have a collision with the electrons that are trying to carry the flow. So as your temperature goes up, your resistance is going to go up as well. Okay, so those are the three aspects of electrical current.